Hi everybody, today we are going to talk about some properties of gases. We want to take a look at how the properties of gases are predicted by the kinetic molecular theory. We're going to define pressure and the units that measure pressure. We'll also take a look at a few gas laws, and then eventually we will solve some stoichiometry problems involving gases. So the kinetic molecular theory for gases, this is a model for how gases work and how they interact together. And so this theory is that particles in a constant straight line will be in motion until they contact their container. So gases will be in motion until they hit something, and they'll move in a straight line until they hit something, and then they'll bounce off. Between molecules of gases, there are no attractions or repulsions, so they collide like billiard balls, or basically they just bounce off of one another, and it's what we would say is frictionless, so they're not losing energy whenever that happens. The space between particles is going to be much larger than the size of the actual particle, so it's not going to be very dense. It's going to be much further spread apart. And then the average kinetic energy from motion is going to be proportional to the temperature of the gas, which we always measure in Kelvin. So when we look at pressure, pressure is explained through the kinetic molecular theory as we look at basically how do particles collide with their container. So they move in straight lines until they collide with either another particle or with their container. And so we look at pressure as force divided by area. The amount of pressure is going to depend upon the temperature, it's going to depend upon the number of particles that are in a container, and then also the volume of the container. So if you have more particles inside of a container, you will have more pressure compared to if you had fewer particles in that same container. When we talk about pressure, we can also look at barometric pressure, which would be what we look at, or atmospheric pressure, which is what we look at with this, where the pressure from the atmosphere will push down on a container of mercury, and then we'll be able to measure how much pressure there is in the atmosphere. Pressure in general is going to flow from an area of high pressure to an area of low pressure, and this flow of pressure is what creates some of the weather patterns that we see. So for vapor pressure, this is going to be, and I believe we talked about this a little bit with intermolecular forces, vapor pressure is going to be the balance between molecules evaporating or vaporizing and then condensing. And so if there's a higher vapor pressure above a liquid, then it's going to prevent the liquid from changing states, or it can also be vapor pressure above a solid. But if the vapor pressure is high, then it's going to prevent the changing of states. So from some units that we use to measure pressure, the most important one, or the one that we use the most, is probably atmosphere. And then we also look at millimeters of mercury. So 1 atmosphere is equal to 760 millimeters of mercury. I would give you conversions here, but we also have units like pascals. So 1 atmosphere is equal to 101,325 pascals. And these are all just different ways that we can look at units of pressure. So of course we could convert between these different units. So if we were converting 0.311 atmospheres to millimeters of mercury, we would use the conversion as shown. And so our problem would look like this. And so we'd be back to our different conversions and the dimensional analysis, I was losing track of my words, dimensional analysis that we've done before. All right, so a few other key things to know when we talk about gases. Oftentimes we refer to something happening at standard temperature and pressure. And when we're referring to gases, what this means is that the temperature is going to be at 273 Kelvin or 273.15 Kelvin. We always use Kelvin for gases because Kelvin's the only temperature scale that does not have negative numbers. And at standard temperature and pressure, the pressure will be 1 atmosphere. This also means then that at standard temperature and pressure, if we have 1 mole of gas, then we will be able to fill 22.4 liters of a container, and also then be at standard temperature and pressure. With pressure, we also look at, based on the kinetic molecular theory, gases don't interact with one another very much, so low intermolecular forces. And because of that, we treat each gas and the pressure that it exerts independently. So Dalton's law of partial pressure says that the total pressure in the container is a total of all of the smaller components within that container. So if we have oxygen and nitrogen, they are each exerting their own pressure. If they're in the same container, then the total pressure would just be those numbers added together. The same thing is true for atmospheric pressure. This is measured in kilopascals, but the pressure of oxygen, nitrogen, argon, water vapor, carbon dioxide, this is going to give us our total pressure of the air.